This is a very recent paper, February-March 2023, paper 42. So we can try some questions together. So what is the situation here? So we have a boat crossing a river. So we have a river. So a boat trying to cross the river. So means the boat is kind of moving in this direction, trying to cross the river. So it travels at a speed of 3.5 meter per second relative to the water. So we can say something like this. Okay. So the boat is trying to move at 3.5 meter per second. But we have a current at right angle to the boat. So for example, the river is kind of flowing this way. So the river flowing is something like this. At right angle, 2.5 meter per second. 2.5 meter per second. So yeah, river current 2.5. By drawing a scale diagram or by calculations. So in this case, we will use calculations. It's easier. Determine the speed and direction of the boat relative to the river bank. So this is a vector problem. So we have two vectors at different angles. So what can we do? So we can set up a triangle. So this is the triangle that we can set up. And then this will be when we have forces at different angles, we have resultant force. When we have speed at different angle, vector, we have resultant. So this will be the resultant. So this is what we want to calculate. So we have right angle triangle. So which means we can use Pythagoras theorem. So here and here, 3.5, 2.5. So we can use Pythagoras theorem to work out the resultant. So it will be something like this, Pythagoras theorem. So we can work out the resultant, which is 4.3 meter per second. So, and then another answer we need to give, determine the speed. So the speed we already have. Direction of the boat relative to the river bank. So this is the river bank here. So means in this direction. We want this angle. Direction of the speed in relation to the river bank. So this is the angle that we want. So again, we can use trigonometry. So we have here and here. So we know this. So this is a tangent situation, tangent relationship. So tangent equals to 3.5 divided by 2.5. So we can evaluate this part. So this will give us angle of 54. So when we have two speed controlling the boat, overall, the boat will be moving in a new speed at a different direction. Not here, not here, but the resultant speed. So that's the idea. So again, we have a vector. So we have the magnitude of the speed itself and also the angle. So this will be the answers we insert here. 4.3 meters per second, angles 54 degrees relative to the river bank. Next part is very straightforward. Speed is a scalar quantity, velocity is vector quantity. State the name of one other scalar quantity and one other vector quantity. So we want one other, so means not this one that we already mentioned. So scalar means we have magnitude only. Vector, we have magnitude and direction. So what are the quantities that have magnitude only? Quantities that have magnitude and direction. So example, distance, time, mass, energy, temperature. So these are all scalars. example of vector. So these are all acceptable answers. Force, weight, acceleration, momentum, electric field strength, gravitational field strength. All of them have magnitude and have direction. Next question. So here we have ship loaded with containers. This ship is made of steel. Density of the steel is 7,800 kilogram per meter cube. Density of water is 1,000. So we can see here, the steel is denser than water. But how come the ship can float? Why does the ship float? Even if water has the steel is denser than the water. So this question is very straightforward. I'm sure you are very familiar. You know why. Because the ship, it is not solid steel. So there are air spaces in the ship. So in terms of actual density, it is denser, but the average density will be less than the density of water. Yes, okay. So these two main points here. Yeah, so this one is for the next question. Yeah, so these two main points here. Next, containers with the greatest mass are loaded near the bottom of the ship. State and explain why the effect on the stability of the ship loading the containers in this way. So we are saying that the heaviest container we will put at the bottom of the ship. So why is this a good thing? Because the center of gravity will be lower. So it will make the ship more stable. Straightforward. Next is a calculation question. A crane lifts container 48 meter vertically upwards. The mass of the container is 30,000 kilograms. Calculate the energy transfer to the gravitational potential energy stored in the container. So this is very similar to the question that we have done before. Very straightforward. Gravitational potential energy, GPE, equals to mgh. So 30,000. G is 9.8. So we can use 9.8 or 10, H 48 meters. So if we evaluate this, we're going to get 1.4 times 10 to the power of 7 joules. So here we will round up to two significant figures. So you can see here, two significant figures. The answer also round to two significant figures. Next question. State the principle of conservation of energy. So this part we need to memorize. Energy cannot be created or destroyed, but energy can be transferred or transformed between energy stores. Next question. A wind turbine has a maximum output power of 1.8 megawatts. The turbine operates at maximum power for 4 hours. Define the unit kilowatt hours. This kilowatt hours is actually energy. Power equals to energy divided by time. So energy equals to power multiplied by time. So this part is power and then hour is time. So we multiply. Normally, power multiplied by time, normally the units is joule. But here, in some situation, we will use kilowatt hour, which is suitable unit for certain situation. So sometimes we use joule, sometimes we use kilowatt hours. So how do we define this? This is the energy transferred. We are talking about energy transferred in 1 hour at a rate of transfer for 1 kilowatt. So we have 1 kilowatt multiplied by 1 hour that will give us 1 kilowatt hours. So energy transferred in 1 hour and then at a rate of transfer of 1 kilowatt. Next, calculate the energy produced by the wind turbine operating at maximum power for 4 hours. Give your answer in kilowatt hours. So we want to calculate the energy. Energy equals to power multiplied by time. So power is 1.8 megawatt. 1.8 megawatt. So we want the answer in kilowatt. So means the 1.8 megawatt, we need to convert to kilowatt. So how do we do that? So 1 megawatt will be equals to 1,000 kilowatt. So this part we need to know that. So 1.8 megawatt, 1 megawatt equals to 1,000 kilowatts. So which means we need to multiply. So we end up with 1,800 kilowatt. So we have the correct unit. 1,800 kilowatt multiply hour for hours. So we have the correct calculations and the correct unit. So that will give us the final answer of 7,200 kilowatt hours. All right. Next question. Radiation from the sun is the main source of energy for most of our energy sources. For example, from the sun, we can get like solar energy, and then we can have photosynthesis, okay, which will give us some the fossil fuels and so on. So a lot of our energy sources coming from the sun. But there are some sources that are not coming from the sun. So we give example. 2 energy sources that are not due to radiation from the sun. So geothermal, nuclear, and tidal. So these are the examples not due to the sun. So we have a metal pan on electric hot plate. So it has 200 cm³ of water. So pan is heated. Temperature in the pan increases. Thermal energy is transferred through the metal pan by conduction. So we know that there are 3 ways whereby heat can be transferred. So we have conduction is one of them. We have convection and then radiation. So in this case, we have conduction because conduction happens when we have direct contact. When we have direct contact between solids, that will be through conduction. So state and explain 2 ways that thermal energy is conducted in a metal. So in a metal, we have 2 ways for the heat to transfer. So for non-metal, we have 1 way only. Non-metal. So we're going to look at the 2 methods. So it can transfer by delocalized electrons. So we know that metals, okay, so structure of the metallic structure, it has many delocalized electrons. So these electrons, they can move through the metal. So when temperature increase, the electrons can move and then transfer the heat. Secondly, we can have lattice vibration. Each atoms, they are vibrating. So when, let's say this atom has a very high energy, is vibrating faster, colliding with the neighbor, it will transfer the heat to the next neighbor, to the next neighbor, to the next neighbor, through the collision. Lattice vibration transfer energy to neighboring particles. So yeah, so this is the idea. So these 2 methods, method 1 and method 2, can happen for metal. But for non-metal, it can use second one only. because non-metals, they have no free electrons. So that's the idea. Next, water boils and leaves the liquid as a gas. In terms of forces and distance between the particles, why gas occupies a much greater volume than the liquid? So this is straightforward. Because attractive forces between molecules in liquid is greater than gases. So particles in gases are much further apart. Straightforward. State two ways in which boiling differ from evaporation. Boiling at fixed temperature only. Evaporation is variable temperature. So for example, water boiling is at 100 degrees Celsius, but evaporation can be 20, 50, 70 degrees Celsius also can happen. Takes place throughout the liquid. So when we have boiling, we have the bubbles coming from the whole liquid. So happens throughout. Evaporation only on the surface, only happen on the surface. Next, final question, calculation. So water is replaced by 200 cm³ of milk. We have the temperature change. We want to calculate the heat capacity. So we make use of this formula. Energy equals to mc theta. So we are given the energy, the input energy. How much energy we have? The mass we don't have, but we have density and volume. So here, what we can do, mass equals to density multiply volume, so we can work out the mass. So C, we want to calculate temperature difference. How much the temperature is changing. So here, so 95 minus 20, so 75. So finally, we can rearrange heat capacity, 60,700 divided 206 divided 75. So finally, that will give us 3.93 unit, joules here, grams here, degrees Celsius here. So the unit will be joules per gram degree Celsius. Let's take a look at the question. Okay, so we are given a semicircular transparent plastic block. So this is what we are given here. A ray of light incident normally on the curved surface of the block. So this is the ray of light that we have. Incident normally on the curved surface. Normally means at 90 degrees. The refractive index of the plastic is 1.5. We are given the information about the refractive index. Let's take a look at the question. Calculate the critical angle for the plastic. So we have a formula for that. Calculate the critical angle. So the formula is this. Refractive index equals to 1 over sine C. Refractive angle equals to 1 over sine C. So C in this case here is the critical angle. So we will substitute. So we have the information about the refractive index, which is 1.5. We will substitute that. 1.5 equals to 1 over sine C. Rearrange. Sine C equals to 1 over 1.5. So C equals to the inverse of sine and then 1 over 1.5. If we evaluate this on the calculator, we will get 42 degrees. So that will be the critical angle. Okay. So what it means by that is that, so this is our block here. So let's say this is the critical angle, 42. If we shine the light at the angle of less than 42, what we will get is refraction. So the light will bend away from normal because we're going from denser to less dense. The light will bend away from the normal. Okay, so as we increase the angle, the light will bend more away from the normal. So as we reach the critical angle, the light will be going parallel to the surface. As we hit the critical angle, so as we go over the critical angle, we will start to get total internal reflection. So that is the idea for the critical angle. So the angle where we get the total internal reflection. Yeah. So the critical angle will be different for different materials. Next question. Okay. On figure 5.1, draw the path of the ray in the block after the ray emerges from the block. Okay, so we are given this ray here. So we want to know what happened. Let me copy the question. What we want to know is this. So we expect the ray will keep going after it enters the block. We want to know what happened when it leaves the block. Okay, so what happened here? Okay, after it re-emerges from the block. Okay, so what we need to do here is first, we already know that the critical angle is 42 degree here. Okay, so we want to know critical angle. How do we measure the critical angle? Is between the normal. Okay, so the light shining. So it's the angle between the light and the normal. So this is the critical. Yeah, so this is how we measure the critical angle. So first, we need to continue the ray. First, we need to continue the ray. And then we want to draw the normal. And then we want to check this angle. Okay? So we want to check whether the incident angle is more than 42 degrees or not. If it is more than 42 degrees, we will have total internal reflection. If it is, so we have three possible answers here. Okay, so we need to check this angle here. Okay, we need to check this angle. So if the angle is less than 42 degrees, we will have refraction. Okay, we will have refraction. If the angle is equal to 42 degrees Celsius, it will be refracted parallel to the surface. Okay. If the angle is more than 42 degrees Celsius, more than the critical angle, then we will have total internal reflection. So when you try to answer the question, the first step is to measure this angle here. Okay, so if you put the protractor here and you measure the angle, you will find that it is more than the critical angle. So if you put a protractor here, let me check the angle. Hold on. Yeah, so you can check the angle with the protractor. So if you put a protractor there, you will find that the angle is 60 degrees. Okay, you'll find that this angle here is actually 60 degrees. So it is more than the critical angle. So what we need to draw here, it will be total internal reflection. So we want to draw the total internal reflection. So what we expect to draw is this. So if we have total internal reflection, then we need to make sure the incident angle and the reflected angle must be the same. So we know the incident angle is 60 degrees. The reflected angle must be 60 degrees as well. So this is how we answer this correctly. If you look at the marking scheme, so this will be the requirements. So ray, first point, the ray continues along the radius of semicircle with plastic. So this part here. So it continues. Okay, no problem. The ray reflected inside the plastic on the straight edge. Okay, with angle of reflection equals to angle of incidence. So it's this part here. Okay, reflected on the straight edge, and then whereby angle of incidence equals to angle of reflection and emerges from the block along the normal. So yeah, so reflected on the block along the normal. So that's the idea. Okay, how we answer this question. Next question. So figure 5.2, we are given a full scale diagram of a lens and an object. So this is what we are given here. Okay. So point mark F shows the position of principal focus. So we have the principal focus here. Determine the focal length of the lens. So for this part, focal length means the distance between the principal focus and the middle of the lens. So this part you will take a ruler and measure it. So you expect to get 7.2 cm here, okay, when you measure it. Second question, draw two rays from the object to locate the image. Label the image I. So for this situation here, we need to locate the position of the image. So this is our object here, where we expect to see the image. Okay, so this is how we can draw the ray diagram. Yeah. So what do we do? First, we draw a parallel line, okay, to the middle of the lens, okay? And then we know the principal focus here. The distance is 7.2 cm. So we can draw equivalent principal focus on the other side, which is also 7.2 cm. Okay, so now we extend this point to the principal focus. So that will be our line. Secondly, we draw another line from the top of the object to the middle of the lens. Okay, so this will be our second line. And then we can see that the two lines, they do not cross. Okay, so normally if we can get the real image, it will cross on the other side of the lens. It does not cross, so which means the image will be on the same side as the object. So how do we find the position? So what we do is we extrapolate. Okay, so we take the ruler to extend this line. We take the ruler to extend this line. And then here, we take the ruler to extend this line as well. So when we extend, we will get the point where it crosses. So that will be the position of the image. So that will be the answer. So this situation here is the magnification. Okay, magnification situation whereby we get the virtual image. Okay, next. So here we have a simplified diagram of the eyes with rays from a distant object and the path of the rays inside the eyes of a person with short sight. So normally, when we try to view the objects, we expect the light to be focused on the fovea, okay, which is right on our retina. So when it focuses here, we will get the clearest image. When we are focused here, we cannot get a clear image. Okay, so in this situation, we need to draw additional lens outside. to correct this short-sightedness and show the path of the rays that are inside the eye. Okay, so what kind of lens we should add? Two types of lens we can add. So we can add the diverging lens or the converging lens. Okay, so in this case, the diverging lens will be the suitable lens. We will see why. Okay, so this is what we expect. So first, we have the problem of the short-sightedness. Okay, so if we put the diverging lens, what will happen? Okay, the diverging lens will disperse the light. Okay, so the light will be dispersed. Okay, so when it reach the eyes, it can form the image further along the way. So it can form the image further along the way, which will be the position that we want, which will give us a clear image. Okay, so that's the idea. So this is how we have the lens to correct the short-sightedness. Okay, so this is what we expect to draw for the answer. Next question is about waves. Okay, some waves have compressions and refractions. Explain what it means by compression and refraction. Okay, let me get a picture. You may recall. So this is the pattern of the sound wave. So the pattern of the sound wave. So we know that sound wave need a medium to propagate. So sound wave, for example, it can propagate in air. Okay. So when the sound wave travel in air, what will happen? So we will have region whereby the air particles are compressed and regions where air particles are away from one another. So this will be the compression region, and then here it will be the rarefaction region. Yeah. So the explanation will be quite clear. So compression means region where particles are closer together than normal, or whereby there is a greater pressure than normal. On the other hand, for rarefaction means particles are further apart than normal or where there is lower pressure than normal. So that's the idea. That's what we are talking about. Next, we can see light from the sun, but we cannot hear any sound from it. Exactly what we mentioned just now. The reason is the light does not need a medium to travel. So the sunlight, it does not need a medium to travel. It's electromagnetic radiation, so it can propagate in vacuum. But sound needs a medium to travel through. But there is no medium between sun and earth. It is just vacuum between the sun and the earth. So we can only see the light, but we cannot hear any sound from it. Next question. During a thunderstorm, an observer sees the lightning almost immediately, but hears the sound of the thunder several seconds later. The thunder and lightning are produced at the same time. The sound of the thunder is heard 9 seconds after the lightning is seen. The speed of sound in air is 300 meters per second. Calculate the distance from the thunderstorm to the observer. So we have the observer here, okay? So we have a thunderstorm here. Okay, so we have the thunder, okay? So happening here, okay? So this is a thunder. So the thunder will produce a light, okay? A light ray to the observer, a light wave, and then it will also produce a sound wave. So the light wave is extremely fast, the speed, okay? So the speed is extremely fast, 3 times 10 to the power of 8 meters per second. So we will see the light almost instantly because it's extremely fast. But the sound wave, the speed is much slower. The sound wave is only 340 meter per second. It is much slower. Yeah, so that's why we will hear it 9 seconds later. Calculate the distance. This is quite straightforward. We can use the formula here, this formula. Okay, so speed equals to distance over time. So now what we need is the distance. Rearrange, distance equals to speed multiplied by time. We have the speed, 340 meters per second, multiply 9 seconds. So that will give us a distance of 3,100 meters. Okay, straightforward. Next question. In a lightning strike, there is a current of 3 times 10 to the power of 4 amperes for 48 milliseconds. Calculate the charge that flows. So for this question, it involves this formula here. Yes. It involves this formula. I equals to Q over T. So current equals to charge divided by time. So means I equals to Q over T. So here we have the current I equals to 3 times 10 to the power of 4 amperes. And time is 48 milliseconds. So for this type of calculations, we need to convert everything to SI unit. So 48 times 10 to the power of -3 seconds. Now we want to calculate the charge. We want the Q, so we rearrange this formula here. Q equals to IT. So I is 3 times 10 to the power of 4 multiply time, 48 multiply 10 to the power of -3. Evaluate this. That will give us 1,400. For the amount of charge, unit is coulomb. Okay, straightforward. Yeah. Next question. Define potential difference. What is the potential difference? Straightforward. Is the work done passing charge through or across a component? Work done per unit charge. Okay, so it is telling us how much energy is needed to push the charge through the electrical circuit. Okay, so we have electrons flowing in the wires in the electrical circuit. So we are thinking how much energy is needed to push this electron. So that's the main idea. Okay. State the equation which defines electromotive force. Straightforward. So electromotive force and potential difference is very similar concept. So electromotive force is the total energy provided to the electrical circuit. So if we have like something like this, a simple circuit. So this part, we will be talking about the EMF, is the energy supply. This part, we will be talking about the potential difference, the energy use. So this is energy supplied. This is energy used to push the electrons around the circuit. Okay? Yeah, so this will be the equation. So equals to EMF equals to the energy divided by amount of the charge. How much energy to push 1 unit of charge across the circuit. Next, we are given some information. EMF of a battery is 9 volt. The battery is in a circuit. Calculate the work done by the battery when it moves a charge of 30 coulomb around a complete circuit. This is quite straightforward. We will be using the formula that we have just now. So, EMF equals to work done divided by the charge. Okay, so we want to calculate the work done. So we are given EMF is 9 volts. The amount of charge, 30 coulomb. We want the work done equals to EMF multiply amount of charge. EMF 9 multiply 30. So here the work done will be 270 joules. Okay, so the idea is like this. If we want to push 1 coulomb of the charge, we will need 9 volts. Okay, if we want to, now we want to push 30 coulomb of the charge, we need more energy. Okay, yeah. So basically that's the idea. So essentially the more charge that we are pushing, okay, no. So this will be hold on. Yeah. So 1 coulomb, we will need 9 joules of energy. Now 30 coulomb, we will need 270 joules of the energy. The more charge we want to push, the more electrons we want to push, the more energy is needed. So that's the idea. Okay. So a circuit consists of a DC power supply, a lamp, and a thermistor. Draw a circuit diagram of these components connected in series. Okay. So thermistor, we know that thermistor is so basically it's a resistor that changes resistance with temperature. So when temperature changes, the resistance will change. So connected in series, we expect to have this. Okay, everything connected in series. DC power supply, the lamp, and the thermistor. So that's the idea. Okay, what happened in the circuit when the temperature of the thermistor is increased? Okay, so this one we need to recall from the notes. In general, the behavior of thermistor is like this. Resistance of thermistor will decrease when temperature increase. So means when temperature increase, the resistance will decrease. Okay, so this is the general behavior. So now, this is hold on. This is our circuit here. Okay, so now we can see that when temperature increase, the resistance will decrease. Let's say initially the resistance is like 5 ohm, 5 ohm. So initial total resistance will be, for series will be 5 ohm plus 5 ohm will be 10 ohm. But now the lamp does not change. It is still 5 ohm. But now temperature increase, resistance decrease for the thermistor. So let's say now it decreased to 3 ohm, for example. So now the total resistance will be 5 plus 3. So the total resistance decrease. So yeah, so essentially what we can see is the resistance of circuit decreases. So this is how the thermistor will affect the total resistance of the circuit itself. When the total resistance decrease, V equals to IR. So when R decrease, the V is constant. Okay, so the power supply is constant. When R decrease, the I will increase, the current will increase. We can see greater current in the circuit. So we expect the lamp brightness will be increased when current increase. So that is the main point there. Okay. Another thing we will see is this greater PD across the lamp. So brightness of lamp increases. Okay. So the idea is like this. The voltage is constant. So like let's say we start with 20 volts. Okay. So the power supply is constant. For series circuit, the energy supply will be shared equally by the two components. So which means initially we have 5 ohm, 5 ohm. They will use up equal amount of energy. So they will use up 10 volts and 10 volts. Okay. But now when temperature increase, resistance decrease. When the resistance decrease, it needs less energy. It needs less energy to push the electron. So now, let's say it reduced to 8 volts. Okay. So here, it will become 12 volt because the total volt will be the same. The total volt will be the same. If here, it uses less energy, here it will use more energy. So that's the idea. So we see greater PD across lamp. So the lamp PD will be increasing. So again, we expect the brightness of the lamp to increase. So that's the idea here. So these three explanations here, we can use either one to explain. Next question. Okay. So we have a horizontal flat coil in a magnetic field. And then we have a power supply here. Okay, we have a battery. So the coil is connected to a cell. The coil rotates. Determine the direction of movement of the side AB relative to the plane of the coil. So we want to determine, okay, the direction of movement. So it will rotate, right? So basically, we want to know whether the rotation is up or down. Okay? So for this, we need to use the Fleming left-hand rule. Okay? So Fleming left-hand rule. So Fleming left-hand rule, okay, so basically is something like this. Okay? So Fleming left-hand rule, all of them, they are 90 degrees. Okay? So if we put our left hand in front of us, so this is what we will see. Okay? So our thumb will be pointing in the direction of the force. Okay? So it will tell us which direction it is moving. Okay? So here, this direction here, it will tell us about the magnetic field, the direction of the magnetic field. Okay? And then here, it will be the direction of the current. Okay? Yeah. So if we look at our scenario here, so we can see the direction of the magnetic field is kind of going in this direction. Okay? So the direction of the magnetic field is like this. Okay? And then the current is like this. So we have positive terminal here. So this is the direction of the current. So direction of the current. Okay. So this is I here. So if we put our left hand pointing these two directions, we will see automatically the last direction will be pointing down. Okay. If we use our left hand. So the force will be in this direction. So we expect the coil to be moving downwards. Okay. So it will be moving downwards. Okay. By using the Fleming left hand rule. How we determine the direction? Okay. Fleming left hand rule. Current, magnetic field, and motion will be at right angles to one another. Yeah. So magnetic field will be from left to right. Okay. North to south. And then current will be from positive to negative. So positive here to negative. Yeah. So that's the main idea. So automatically, the last direction will be the F, which is pointing downwards. Next, state and explain what happened to the coil as it reaches the vertical position. So essentially, when it reaches the vertical position, it will stop. Or at the vertical position, it will overshoot and comes back. Okay? Because the yeah. So when it goes, so basically when it goes to the vertical position, now the magnetic field is reversed. Okay? So now when the magnetic field is reversed, the direction of the force, it will reverse. So that's the idea. Okay? So what we expect here. So the coil, as it approaches the vertical, the turning effect will be decreasing. And then finally, when it reaches the vertical, the turning effect will be 0. And then when it passed the vertical, the turning effect will be reversed and changing direction. Because now it is experiencing the opposite direction of the magnetic field. So that's the idea. Yeah. So if we want the coil to keep moving, for example, in clockwise direction, so we don't want it to go back and forth. We don't want it to overshoot and come back. We don't want it to go back and forth. We can put the split ring commutator. The split ring commutator. Okay? So what it will do? Okay? So the split ring commutator here. Okay? So it will change the direction. Okay? Of the power supply. Okay? So at each turn, it will change the direction. So it will ensure the current is maintained in the same direction so that the coil can rotate continuously in the same direction. Okay? At the same time, without getting the the wires tangled. Essentially, it reverses the current at every half turn. So that's the idea. Okay. Next question. Here, we have a nuclear power station that has a reactor where control nuclear fission of uranium-235 takes place. Explain what is meant by the nuclear fission. Nuclear fission means we take a nucleus. What do? We will break the nucleus into smaller atoms. Okay, essentially, this is what we are doing. Okay, we take large unstable nucleus, and then we split into smaller nucleus to release energy. So this is the idea for nuclear fission. We have another type, nuclear fusion, whereby we fuse together smaller nucleus to form a larger atom. Okay, so in both cases, energy will be released. Okay, Because energy is released, we can use this idea for generating electrical power. Because energy is released, we can convert the nuclear energy into electrical power. We have some advantages and disadvantages for this method of generating electrical energy. Advantage, okay, continuous supply of energy. Okay, so essentially, if we keep adding the nuclear reactants, okay, then we can get then the nuclear reaction will keep going. We can get continuous supply of energy, not affected by weather, okay, not affected by wind strength, okay. Here we are comparing electrical power generated using wind turbines, okay. So if we compare to wind power, this will be the advantage, continuous, not affected by wind strength, produces large amount of energy, okay. So nuclear reaction can produce a lot of energy, okay. Disadvantage, resource finite, not renewable, okay. Because for example, let's say we are using the uranium, okay, atom, the radioactive uranium to generate the nuclear energy, it depends of the uranium. If we run out of the uranium, then we don't have any more. So this is not renewable. Very expensive to build the nuclear power plant and difficulty of decommissioning. So when we want to stop using the nuclear power plant, it's very difficult to close it down because we have a lot of nuclear waste. Danger if any leak or of radiation. Okay, so it can produce some harmful radiation. Okay, if it is leaked out, then it's quite dangerous. And then it can produce hazardous waste. Okay, so when the uranium break down, it will produce the nuclear waste, the other atoms that can be quite dangerous and very difficult to convert it to harmless material. Yeah, so basically very difficult to store the used radioactive material, and the nuclear waste must be stored for a long time. The storage is very difficult. Okay, next, deuterium. Deuterium is an isotope of hydrogen with one proton and one neutron. Nuclear fusion occurs when two nuclei of deuterium combine. An isotope of helium and a neutron are formed. Use nuclide notation to write down the nuclide equation for this reaction. Okay, so this is another example where we have a smaller atom. Okay, so smaller atom fuse together to form a larger atom. Okay, so it will look like this. Okay, so we have deuterium. Okay, deuterium, hydrogen is like this. Okay, deuterium means, so hydrogen is one proton only. Okay, but deuterium has one proton and one neutron. So the mass number is 2. The proton number, it is still 1, but the mass number is proton plus neutron. So the mass number now it is 2. So this is nuclear fusion. We fuse together smaller atoms to form a larger atom. Okay? Yeah. So it forms a neutron as a byproduct. Yeah. So this is what we expect to happen here. This is the last question about space physics. Time taken for Mars to orbit the Sun is 690 Earth days. The average orbital radius of Mars is 2.28 times 10 to the power of 8 kilometers, and Earth day is 24 hours. Calculate the average orbital speed of Mars in kilometer per second. Okay, so the idea is like this. Okay, so we have the Sun. Okay, so this is the Sun, and then we have the orbit. Okay, so the Mars is orbiting around the sun. Okay, so it's moving around the sun. Okay, over time. Okay, and then we know the Earth is like somewhere here. Okay, so the Earth has a smaller radius compared to the Mars. Okay, so which means we know the Earth, okay, will take a shorter time to orbit the sun. Okay, so for the Earth, it will take 1 year to orbit the sun. Okay, but for the time taken, so for Earth will be 365 days to orbit the sun, but for the Mars will be 690 days. Okay, so makes sense. Mars is further away from the sun, so it will take longer time for it to orbit the sun. Okay, no problem. Okay, so our objective here, okay, is this. We want to find average orbital speed. Okay, so we want to know how fast it is moving. Okay, around the sun, how fast it is moving. Okay, speed. Okay, so now what we do is the formula is very simple. Okay, essentially what we have is speed equals to distance divided by time. Straightforward. Okay, so what we want to calculate is the speed. The distance, what kind of distance it is moving? The distance is the circular orbit around the sun. So this is the distance. Okay, so one round, it moves a full circle. So the distance, it will be the circumference. The circumference of this circle. So we know the formula to calculate the circumference of a circle, which is 2 pi r. R is the radius. Okay, so essentially, we have the distance moved is the circumference, which is 2 pi r divided by the time. So that's the idea. Okay, very straightforward. But what we need to do is we need to pay close attention to the unit. Okay, so it's km per second. So which means we need to give our calculate in our distance in terms of km, and then we need to give our time in terms of seconds. Okay, so now okay, give some space here. Okay, so now our 2 pi r, okay, we can substitute. So the speed equals to 2 pi r. 2 pi, the radius. The radius is given here. Okay, 2.28 times 10 to the power of 10 to the power of 8 kilometers. That's good. It is already in kilometers. So we can substitute it right away. It's already in kilometers. So we can substitute right away. It's already in the unit that we want. Okay. So this part will be in kilometers. Okay. But the bottom part, we want it to be in seconds. But here, the time taken is 690 days. So the 690 days, we need to convert to second. 690 days. Okay, so we can use the conversion factor. Okay, so 1 day equals to 24 hours. Okay, 1 hour equals to 60 minutes. Okay, 1 minute equals to 60 seconds. Okay, so this works out. What we can do here, we can cross out the units that we don't want. Okay, it gets crossed out. Okay, so finally we are left with seconds, which is what we want. Then we can finish the calculations. So what we have there, 690 multiply 24 multiply 60 multiply 60. So that's what we have here. 690 multiply 24 multiply 60 multiply 60. So that will give us the unit of seconds. Okay, so if we evaluate everything, that will give us 24 km per second. Okay, so this is what we want, okay, for these calculations. State the shape of the orbits of the planet. Okay, so we can see that for this calculation here, that our assumption. The orbit is a perfect circle. That's our assumption. But in reality, it is not a perfect circle. Okay, it is elliptical. Okay, so if we view from the top, we might expect that it is a perfect circle, but in reality, it is elliptical. Okay, yeah. Okay, but to simplify things, normally when we do the calculations, we will assume that it is a perfect circle. Okay, light from a distant galaxy is redshifted. Explain what is meant by redshift. Okay, this is the idea. Wavelength of light from distant galaxies increases, occurs when galaxies are moving away from Earth. Okay, so yeah, the idea is like this. Okay, so if we have Earth here, and then we have a star, we have another star here. Okay, so the star will shine light. Okay, okay. So let's say the light is like uh 500 nanometer, something like this. Okay. But what we measure here, okay, we expect the light to be 500 nanometer, but what we actually measure is like 600 nanometer. Okay. So this is quite weird. We expect the light to be 500 nanometer, but what we actually measure is 600 nanometer. So this is what we're talking about. The wavelength increases. Okay. How can we explain this increase in wavelength? It is when the stars are actually moving away from us. Okay. So as it is moving away from us, the distance is increasing. Okay. The speed of light is constant. When the distance is increasing, okay, means the wavelength, it will increase. Okay. So that's the idea. Okay. Yeah. So basically, it's the same wave, but it need to travel a longer distance. Okay. What we detect is actually the wavelength increasing. So that's the idea of the redshift. Okay. State the quantity that the redshift of a galaxy is used to calculate. Yeah. So this one we will look into more detail later. Essentially, okay, we can measure the speed or the velocity that the galaxy is moving away from Earth. Okay, by measuring how much the redshift, it can give us some information. How fast the galaxy is moving away from us. Okay, how fast the star is moving away from us. Okay, so this is not just one star moving away from us. It's like everything moving away from us. It's telling us that the universe, it is expanding over time. Okay, we don't know for sure, but at this moment, this is what we know for now. Okay, based on our measurement, we think that, okay, everything is moving away from us. Is that the universe is expanding. Okay, so this paper is done.